Okandan'la beraber çalıştık. Melin Bilkent Üniversitesi'nde matematik çalışıyor. Onunla beraber Error Correction Codes çalışmıştık. Özellikle de Cyclic kodları üzerine durmaya çalıştık. Şimdi Melin bize 17 dakikalık konuşmasını yapacak. Hazırsan başlamayalım.
Hey everyone, today I'm going to make a presentation about error correction codes, as my mentor mentioned. So let me get started with. So what is our problem here? We want to send a message to a receiver, and we want to send this message in an error-free way. So what do we mean in detail? We have an information source that sends the message, which gets encoded, and then this message travels through a noisy channel. And in this channel, our message can get some errors. And it gets decoded, and then the receiver receives a message. What can be this noisy channel? For example, it can be the thin air, or it can be the cable that sends our messages. But our problem is, how do we fix the errors occurring here? Before diving deep into this question, let us define some basic things. Let A be a finite set. Now, we are defining a code C of length 10 as a set of words of length 10. That is, C is a subset of the Cartesian product of A n times, and the elements of C are called code words. For example, English verse of length 5 is actually a code. And apple is a code word in this code because it is a length 5 word and it's in English. And if you were to look at a more mathematical like 0,1, then C equals 0,0,111 is actually a code because it is a subset of the Cartesian product of A 3 times. And 0,0,0 and 111 are code words in this code. Now, I want to note that we do not just want to construct any code. We want to construct codes that can detect and correct errors, an efficient code, which is what we are seeking. And by Shannon's theorem, we are guaranteed that we can always find such an error correcting system. What does this Shannon's theorem say? Assume we have a discrete channel that has capacity C, and if we have the entropy H less than or equal to our capacity, we know we are guaranteed that there is always a coding system which can help us transfer our messages in an arbitrarily small amount of errors. So we can look into some methods that can be used in error correction. Let's start with channel coding. How does this procedure work? Assume that we have a message that consists of zeros and ones only. If the message has an odd number of ones, we add 1 at the end of our message. And if it has an even number of ones, we add 0 at the end of the message. Let's look at this example. Assume our message is 1101. Here you can see there are 3 ones in our message. So this is an odd number, and we are adding 1 at the end of it. So we are actually sending 11011 instead of sending 1101. Now, if the receiver has an error, he or she will know it. Now, assume that this is the errored message, 10011. How they will know that there is an error? Because except the last bit, as you can see, there are 2 ones. So the last bit should have been 0, but instead it's 1. So we can detect errors using this systems, using this channel coding system. This is an advantage of it. But as you can see, this channel coding does not say anything about the placement of the error. It just says there's an error and that's all. But this is not enough for us. So if we want to deepen our study of error correction systems, let's look at linear codes. We are focusing on linear codes because linear codes are actually linear subspaces, and linear subspaces always have bases that can be easily constructed, and it allows us to have more information about the structure of our code. Let's define it mathematically. A linear code C of length 10 and rank K over a finite field Fq is actually a subspace of the field Fq to the power n. Now, if Q equals to 2, we call it a binary code, and if Q equals to 3, we will say that it's a ternary code. As I said, being a vector space is an advantage here because we can describe the linear code using this basis. And what is more, the encoding and decoding procedures are faster than nonlinear codes here, which is an important factor because we will maybe use it for communication, and the fastness is important for us. But we want to know even more about the structure of the coding system we are working with. So we are defining something called cyclic codes. Before saying more about the motivation why we are studying this, let us define it mathematically. A linear code C in Fq to the power n is cyclic if any cyclic shift applied to a code word is again a code word in C. What is a cyclic shift? Assume that we have a code word C0, C1, C up to Cn-1 in C. Now, if we were to apply the cyclic shift, we move each coordinate of this code word to the right except the last coordinate, and we are sending the last coordinate to the first coordinate. So we are obtaining Cn-1, C0, up to Cn-2. If it is again a code word in C, and if this applies for each element in our code, we say that our code is cyclic. For example, take this example. Let's C equals 0, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1. Let's take an element here, 1, 1, 0. If we were to apply a cyclic shift to this element, we would obtain 0, 1, 1. But you can observe that this 0, 1, 1, look at each element of C and apply the cyclic shift. You would again remain in C, which makes this code cyclic. Now we can say more about the motivation. Now it is the same to study cyclic codes and some types of ideals. In these ideals, we know more about the structure. What do we mean by the structure? For this, we need mathematics. Let's define it. Let Rn be the quotient ring such that Rn equals fqx divided by the ideal generated by x to the n-1. Now fqx is the polynomial ring in which the polynomials take their coefficients from the finite field q. And we are dividing this polynomial ring to the ideal generated by x to the n-1. So you can think of it as we are looking at elements modulo the polynomial x to the n-1. Let's define a map theta. This theta takes vectors from fq to the power n and sends this to Rn such that theta maps a code word a0, an-1 to a0 plus a1x plus plus an-1 x to the n-1. You can see that each coordinate will be the coefficient of an element here. For example, a0 will be the constant, a1 will be the coefficient of x, and ai will be the coefficient of x to the power I. You can observe that theta is an isomorphism and theta c is an ideal of Rn. We can see through this picture, we are taking a linear subspace, a cyclic code from fq to the power n, and this theta sends it to an ideal of Rn. And this theorem summarizes it. A linear code C is a cyclic code if and only if theta c is an ideal in our quotient ring Rn. We know what a cyclic shift means in the linear subspace C. What does it mean in the polynomial ring? It takes the element a0 plus a1x plus so on to an-1 plus a0x plus plus an-2 times x to the n-1. It sends it this. Now, if we were to multiply x with the first thing we had at the beginning, we would again remain in our ideal, remain in our subset. This makes it an ideal because when we multiply x with an element in our set, we are still remaining in our ideal. How do we have this? Because the only problematic thing in this multiplication can be the term an-1 times x to the power n. But this again equals an-1 because, as I said before, we are looking at things modulo x to the n-1. So let's take an example. Consider the code C equals 0, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1. Well, this is the same cyclic code we studied before. Now observe that C is a subspace of f2 to the power 3. Here n equals 3 and q equals 2 because the elements of the code word are zeros and ones. There are two things in our finite set, and the length of the code word is 3. This makes n equals 3. So by the above theorem, we have that our cyclic code C is actually isomorphic to an ideal of f2x divided by the ideal generated by x cubed minus 1. What is more, we can write down precisely what are these elements of our ideal. How do we do that? For example, 1, 1, 0 will be corresponding to 1 times 1 plus 1 times x plus 0 times x squared. So this will give us x plus 1. We will obtain from 1, 1, 0 the element x plus 1. If we were to do this for each element of C, we will obtain a complete list of our ideal I. Now, so far, so good. We have said so much about these ideas, so we are ready to state this theorem. Assume that C is a non-zero cyclic code in Rn, and there's a polynomial gx in C with the following properties. First of all, gx is the unique monic generator of minimum degree in our code C, which means that we can generate our cyclic code C using this polynomial gx. What is more, gx divides x to the n minus 1, and if we were to let k equals n minus the degree of g of x, we can say that the dimension of our cyclic code c is k, and write down the complete basis of it. This basis is gx comma x times gx comma dot 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 comma x to the k minus 1 times gx. And since it is the unique monic generator of our cyclic code c, we can write each element in c as a product of gx and another polynomial f. And by the above items, we can say that f is either 0 or degree of f is less than k, because we know that the dimension of our cyclic code cannot exceed k. Well, having a generator polynomial eases our work in working in this coding system. But besides the generating polynomial, there are many other polynomials that can be used to generate a cyclic code. And this makes it even easier to work with cyclic codes. What do we mean by this? Let us define some things to understand what does this mean. An element E of a ring satisfying E squared equals E is an idempotent. Now the ring Rn is semi-simple when n and q are relatively prime. Now this will allow us to separate our ring into minimal ideals, because we are working in a semi-simple case, so we are allowed to separate our ring into minimal ideals. Now by the Wedderburn structure theorems, each cyclic code in Rn contains a unique idempotent which generates the ideal. So here, this theorem summarizes it. Assume that C is a cyclic code in Rn. Then we know that there is a unique coidempotent in C such that C is generated by this idempotent. What is more, if we know that C is generated by this idempotent, we know that this idempotent Ex is the unity of C. And if we know what the unity of C is, we know this idempotent will be generating our cyclic code. So we have so much information about how to generate C. But we can still define some more. Again, let's say the greatest common divisor of Q and N to be 1. This means that x to the n minus 1 can be written down as a product of irreducible distinct factors. Then let's say x to the n minus 1 equals f1x times f2x times dot 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 times fsx, where fi's are distinct and irreducible over fq. Now we are to define a new polynomial fi hat x. Let fi hat x be the polynomial that is obtained by dividing x to the n minus 1 to one of its irreducible factors fi. Now what is a minimal ideal? A minimal ideal, an ideal is called minimal ideal when there is no ideal properly contained between 0 and our ideal I. Well, ei hat x will be denoted to be the generating idempotent of the ideal generated by this polynomial fi hat x. So we are having an ideal which is generated by this newly defined polynomial, and we are calling this idempotent ei hat x. So let us take this theorem that will allow us to know much about the structure of our Rn. First of all, the ideals generated by the polynomials which we newly defined fi hat x are all the minimal ideals of Rn. We do not only know that these, you notice that we do not only know that these are the minimal ideals, we know that they are all of them, and we constructed them, so we know how they work. What is more, we know that Rn is the vector space direct sum of these ideals generated by fi hat x. So we can describe our quotient ring only using these structures we know about. We can sum them and we will get Rn. Now we have some things to say about the generating idempotence of this fi hat x. Now if I does not equal to j, we know that ei hat x times ej hat x will be always equal to 0 in Rn. And if we were to sum all these generating idempotence, we will get the multiplicative unity of Rn. So we can express the multiplicative unity of Rn by summing up these generating idempotence. And the only idempotence in the ideal generated by fi hat x are 0 and ei hat x. What does this mean? This means that if we run into an idempotent in our ideal, we will know for sure that this idempotent will be surely generating our ideal. Okay. And there's something more. If we, let's say we take an arbitrary idempotent in Rn, not just in our minimal ideals, we are just taking a random idempotent in Rn. Then we know that there is a subset T of the integers 1 through s, such that Ex can be expressed as a sum of ei hat x. And the ideal generated by Ex can be expressed as a sum of the ideals generated by fi hat x, in which the I is taken from this subset of integers. So working in the semi-simple case, we were allowed to examine our structures into minimal ideals. Now we are using idempotence instead of generating polynomials, and observe that by the last item, we are allowed to describe any ideal, anything in Rn by this idempotence. This is why we work with idempotence at the first place. So we haven't talked it about here, but we can generate this idempotence using the generator polynomials, and there are other ways that are not using these generator polynomials to construct this idempotence too. So it is very easy and efficient to work in the cyclic code space. This is why in the first place we started working with it. So this was all about the cyclic codes, but for further studies there are some questions to think about. Well, what if we see these subspaces of vector spaces as ideals of group algebras? Notice that in this work we only focused on ideals of a quotient ring, Rn. It's a specific type of quotient ring. What if we were to focus on the ideals of group algebras? What would be the advantages and disadvantages? Now, another question can be, as you can see, linear algebras contain abelian groups such that cyclic codes and group algebras are both isomorphic to them. Okay, we know this, but are there any non-abelian groups that will be efficient codes? Well, we are thinking ways to again construct efficient codes. So can this be the way? Can non-abelian groups satisfy this? A more general question can be, what are the other algebraic structures that can help to build efficient coding systems? Well, this is a very general question to be answered, but yet it expects an answer. So this is the end of my presentation. I want to thank especially to my mentor who supported me through this journey, and thank you all for listening.
Melin'e bu bilgilendirici ve keyifli konuşması için teşekkür ederim. Çok teşekkürler. Çok keyifli.